Hello, in this video we're talking about Gibbs free energy starting on the bottom of page 41, continuing through page 44. So Gibbs free energy has to deal with thermodynamically favorable processes. If we have a thermodynamically favorable or spontaneous process, that means that it is taking place without any net input of energy from an external source. All the energy that is needed is coming from within that thermodynamically favored process. Whether or not a process is thermodynamically favorable depends on both entropy and enthalpy. So we have a combination of the two, and that is called Gibbs free energy. Gibbs free energy, or delta G, is the amount of work that can be obtained from a process when we're at constant temperature and pressure. So Gibbs free energy, it's talking about the amount of energy that's available within the system to do work after you've taken into account the enthalpy and entropy changes of that system. So we have an equation here that we can use to calculate delta G when we have entropy and enthalpy, since again, whether a reaction is thermodynamically favorable depends upon both of those things. Temperature also plays a role in here as well. This formula is on your formula chart, where delta G is our Gibbs free energy. Delta H is the enthalpy change. Generally, enthalpy change is measured in kilojoules per mole. And then we have minus T. T is our temperature in Kelvin, so do make sure that's in Kelvin. And then delta S is that entropy change you saw in your last video lesson. That usually has units of joules per mole Kelvin. Notice that the units for delta H and delta H are different. We have to make sure both units are the same before we go and calculate delta G. We normally end up converting delta S to kilojoules rather than joules to solve for delta G in kilojoules, since that is what it is generally measured in. Whenever we calculate, the sign of delta G is going to tell us if a process is thermodynamically favorable or not. So we saw this back in our electrochem unit as well. A negative delta G means that our process is thermodynamically favored. Another term that we see for that, in addition to spontaneous, is exergonic. So thermodynamically favorable or negative delta G is exergonic reactions. If we have a positive delta G, we are not thermodynamically favored. The reverse reaction is going to be thermodynamically favored, though. That would be the spontaneous reaction, not the forward direction. Positive delta G can also be called endergonic when we have that non-spontaneous reaction. And lastly, when we have a delta G of 0, that just simply means we're at equilibrium. Neither direction is favored more than the other. We can calculate the Gibbs free energy of a reaction, the standard Gibbs free energy, or delta G naught of our reaction, using the standard free energy of formation of the products and reactants. We have seen equations super similar to this with delta H as well as delta S. So it's the sum of all the Gibbs free energy of the products minus the sum of all the Gibbs free energy of the reactants. This equation is on your formula chart as well. For delta G, elements do have a value of 0 because forming an element itself is going to have no change in the Gibbs free energy. So elements are going to be 0 in their standard state for both enthalpy and Gibbs free energy. But remember, elements are not 0 for our change in entropy. 0 entropy would be a perfect crystal at 0 Kelvin, and remember, nothing actually falls into that category. Everything will have a entropy that is greater than 0. Since Gibbs free energy depends on both the delta H, the delta S, as well as the temperature a little bit, our reaction can be driven by enthalpy or entropy, or even both, depending on what is favorable in nature. Nature favors an increase in entropy, or positive delta S. Remember, the second law of thermodynamics says that all spontaneous reactions are going to have an increase in entropy of the universe. So if we have a greater disorder of our particles after our reaction, that is what nature favors. Nature also favors an exothermic reaction, or negative delta H, which is that release of energy. When we release that thermal energy, the temperature of the surroundings increases. If the temperature of the surroundings increases, the particles are moving faster, they have greater kinetic energy, the entropy of the surroundings is increasing. So when both of these things are happening in conjunction, there's going to be an increase in entropy of the universe. The positive delta S means our system or our reaction is getting greater disorder, and the negative delta H releases that energy to the surroundings. If our surroundings gain energy, they are gaining entropy as well with that temperature increase. For a reaction to be thermodynamically favorable, or to have a negative delta G, entropy doesn't have to be increasing, and our reaction doesn't necessarily have to be exothermic for a reaction to proceed. If one or the other is favorable enough to outweigh the unfavorableness of the other, the reaction can in fact be spontaneous. So let's look at a few examples of that. Whenever a reaction is only driven by enthalpy, so enthalpy we want to be negative. That's what nature's favored, is that negative delta H. If we have an extremely exothermic reaction, even if there is a decrease in entropy or a negative delta S, which nature does not favor, it can still have a negative delta G, provided that the temperature is low enough. So, for example, the formation of our sodium chloride solid from its elements is spontaneous. It releases a ton of heat. Because it's releasing lots of heat, we have that negative delta H, but we're going from 2 moles of a solid plus a mole of a gas to 2 moles of just a solid. That's a negative delta H. So our enthalpy is favorable to nature, but our entropy change is not. Because we have that decrease in entropy, but it's highly exothermic, that negative delta H part of our delta G equals negative H minus T delta S is negative enough that whenever we subtract, or we're subtracting a negative, so adding this T delta S factor, our negative is still bigger than the part that we're adding, so the overall delta G will still be negative. The reaction will still be thermodynamically favorable. The same is true when we're driven by entropy, just a little bit opposite. If we have an endothermic reaction, so that's our negative delta H, that is not favorable to nature. But if we have a high enough increase or a high enough positive entropy, that is favorable to nature. So if our highly positive delta S outweighs the fact that it's endothermic, it can still be a spontaneous reaction. So for example, as sodium nitrate dissolves in water, there is a decrease in temperature. If it's getting colder, that means that we have a positive delta H that is not favorable to nature. But we're going from solid to aqueous. Aqueous substances have more particles, more entropy, so we have that decrease in entropy, which is favorable to nature. So since entropy change is favorable to nature, this reaction is driven by entropy. If we look at our delta G equals delta H minus T delta S, delta H is positive. We're subtracting another positive factor here, but this positive factor that we're subtracting is bigger than the positive delta H because our entropy change is driving that reaction, so the overall delta G ends up negative, making the reaction thermodynamically favorable. So we need to be able to use the signs of delta S and delta H together to figure out if a reaction is going to be spontaneous or not qualitatively. So that means without the numbers. And we do need to consider their relationship within our equation delta G equals delta H minus T delta S. We can show this graphically with our graph. So let's talk about what that means. We're first going to set up our coordinate planes. Is the order that we need to use, meaning that we're going to start with delta S up top and delta H to the side. So as we go from S to H, that is our graph there. In the upper right-hand coordinate, this is where delta S and delta H are both positive. So if we look at our x axis here, this would give us a positive delta H value there and a positive delta S value. If we have a positive delta H, that is not favorable, but a positive delta S is going to be favorable to nature. So if this reaction is spontaneous, it's going to be driven by entropy. And again, it would be driven by entropy because positive delta S is favorable to nature, whereas positive delta H is not. If this reaction is spontaneous, though, it is temperature dependent. It is temperature dependent because in order to get that negative delta G, the factor that we are subtracting here from our positive delta H must be larger than the positive delta H to end up with our negative delta G. So temperature is a varying factor there. As we increase temperature, that's going to increase this minus T delta S factor. When it's greater than the delta H factor, we end up with that negative delta G. So if we have a positive delta H and a positive delta S, this reaction will only be spontaneous at high temperatures. So as we continue to move around our coordinate plane, in the bottom right-hand corner, delta H on the x-axis is still positive, whereas delta S on the y-axis is going to be negative. While positive delta H is an endothermic reaction, that's not favorable to nature. Negative delta S is a decrease in entropy. That's not favorable to nature either. If we have a positive delta H and a negative delta S, those sorts of reactions will never be favorable. Continuing around, we have negative and negative for both delta H and delta S in the bottom left-hand corner. Well, negative delta H is an exothermic reaction. That's favorable to nature. But our negative delta S, that decrease in entropy, is not favorable to nature. So if one or the other is favorable, it's going to be temperature dependent again. If it does end up being favorable, it is going to be driven by enthalpy. It is driven by enthalpy because, again, exothermic is favorable where that decrease in entropy, the negative delta S, is not. So if we take a look at our delta G equation again, in order to have a negative delta G for that spontaneous reaction with the negative delta H and a negative delta S, our negative T times the negative delta S is going to give us a positive T delta S factor. Well, if our temperature is too high, that factor that we're adding to our delta H would make delta G positive. But whenever our temperature is low enough, we're adding a small enough number to our negative delta H so that it is not larger than that negative delta H, we'll still end up with a negative delta G. Whenever we have a negative and a negative for both enthalpy and entropy, it will be favorable at low temperatures. Lastly, in the upper left-hand corner of our coordinate plane, we would have a negative delta H and a positive delta S. Negative delta H or exothermic reaction is favorable to nature. A positive delta S or an increase in entropy is favorable to nature as well. If both of these factors are favorable to nature, these reactions will always be spontaneous. So when it comes to tests and quizzes, we need to know this relationship so we can kind of simplify our coordinate plane. For those purposes, it's our graph, so S to H. Whenever in the upper right quadrant, it will be favorable at high temperatures. In the lower right, it is never, so that's when it's positive, negative. Whenever we're negative, negative, it is favorable at low temperatures. And whenever we're negative, positive, it is always favorable. This exact same information can be considered in a table as well, like we see here. Whenever we have a negative delta H and positive delta S, it is favored all the time since both of those are favorable to nature. If we have a endothermic reaction with a decrease in entropy, that is never going to be favorable because neither of those are favorable to nature. Then we got some typos in our table here. Whenever we have a negative exothermic reaction, which is favorable, but a negative delta H, which is not favorable, we are going to be favorable only at low temperatures. So low temperatures will give us that negative delta G. And whenever we have a positive delta H, which is not favorable, but a positive delta S, which is favorable, will be favorable at high temperatures whenever our temperature is high enough to get us that negative delta G there. If we have a negative delta G, our reaction is spontaneous, it's thermodynamically favorable, but it doesn't mean that it necessarily always happens. Sometimes a reaction can happen so slowly that we don't actually make a measurable amount of products. Whenever that happens, it's because we have a very, very high activation energy. So it's really hard for our reaction to actually achieve that reaction energy in order to start. So we're going to learn more about that in our kinetics unit in Unit 5. But whenever this happens, we say that our reaction is under kinetic control. If we have a non-spontaneous reaction, we can force it to happen. There's a couple ways. We've all actually learned one way already, and that was in our electrolytic cells through the process of electrolysis, where we're applying an external source of energy. So providing that energy into the system like we do in electrolysis reactions, we're able to get that to happen. We can also couple thermodynamically favorable reactions with the unfavored reactions in order to get a overall negative delta G. So for example, glucose and fructose forming sucrose is not favorable. But if we pair it with our ATP reaction here to ADP, which is favorable, that negative delta G, we can add up those delta G values like we do similar to Hess's law, and we get that overall negative delta G. So this overall reaction is spontaneous, and we're still making that product that we want here. So let's look at some practice problems here. Given the values for delta H, delta S, and our temperature below, we want to know which sets of data represent thermodynamically favorable processes. Well, we can initially look at this and figure out if it's always or never spontaneous, but sometimes it's going to depend on temperature. If it depends on temperature, we're going to need to calculate whether our delta G is negative or positive using our delta H minus T delta S equation here. So as we look at our first set of data at A, we have a positive delta H and a positive delta S. Well, positive delta H, not favorable. Positive delta S, yes, favorable, so it depends on temperature. Positive, positive, we're favorable at high temperatures, but that's kind of all relative. So here we're going to need to use our equation to actually calculate that delta G. So for delta G, we have delta H, which is our 40 kilojoules, minus our temperature in Kelvin, it already is, so 130 Kelvin, times our delta S, Remember, our units for delta H and delta S are generally going to be given to us differently. We're going to have to convert those delta S units to kilojoules by dividing by 1,000. So we have 0.300 kilojoules per Kelvin for that delta S there. When we do this math, that's going to give us 1 kilojoule. That is a positive delta G. If we end up with a positive delta G, this is not going to be thermodynamically favorable. When we look at B, though, it's still the same delta H and delta S, so it's temperature dependent again, but now it's a higher temperature. Positive is favorable at higher temperatures, so let's plug it all in and see what happens. So here, the only thing that's changing from A is that temperature. We're at a higher temperature because this factor that we're subtracting now is greater. We end up with a negative delta G. So yes, B is going to be a favorable reaction. It would be a favorable reaction that is driven by entropy, since our positive delta H is favorable to nature, but that positive delta H is not. If we look at C, we have a positive delta H, that's not favorable to nature. A negative delta S, that's not favorable to nature either. Neither of these are favorable to nature. This reaction can never be spontaneous. Go ahead and take a moment and look at D and E to determine if these reactions are favorable or not, and resume the video when you're ready to check. In part D, we had our negative delta H and negative delta S. Negative delta H is favorable, but negative delta S is not. We're going to have to solve for that delta G. Plugging that in, we get a negative 1 kilojoules per mole. So our temperature was low enough for our reaction to be spontaneous. This reaction would be driven by enthalpy because enthalpy is favorable, whereas our entropy, or delta S, is not. When we look at E, we had negative delta H and positive delta S. Both of those are favorable to nature. This reaction will always be favorable. Moving on to number 2, we want to calculate delta G for our reaction using the delta H and S information that is given here. We're given delta H and delta S for just the different reactants and products of our balanced chemical equation. We're going to need to use our products minus reactants to solve for those two things. Once we have our delta G and our delta S, we can then use our delta G equals delta H minus T delta S to solve for those. So take a moment, try that out, and resume the video when you're ready to check. So first, we need to solve for our delta H of reaction using products minus reactants, remembering that our elements in their standard states are 0. We get negative 548 kilojoules per mole. Next, we needed to solve for our delta S. This is also going to be products minus reactants, but now our elements are not 0. We'll be using all those values from the table, and we find that our delta S is a negative 38. So we have a negative exothermic reaction, which is favorable, but a negative decrease in entropy, which is not favorable. To figure out our delta G and if this reaction is spontaneous or not, we're going to need to use our delta G equals delta H minus T delta S equation here. But remember, we have to make sure our units are matching. Delta H is in kilojoules, that delta G is in joules, delta S is in joules. We're going to need to convert that to kilojoules. Whenever we have kilojoules per both, we can go and plug everything in to solve for delta G. So we should find that delta G is negative 537 kilojoules per mole reaction. So this is a thermodynamically favored reaction that is driven by enthalpy, since our negative exothermic enthalpy is going to be favorable, while that negative delta S is not favorable to nature. So moving on to our last problem here, we want to calculate our equilibrium constant K, given the value of delta G that we just calculated. We want to know if the reaction is thermodynamically favorable using both our delta G and our equilibrium constant to justify that answer. Give that a try on your own and resume when you're ready to check. So we have this equation, delta G equals negative rat length, that we learned back in our electrochem unit. We're going to need to use this, plug in our delta G, and solve for K. And we want to make sure remembering unit-wise is we have to use our delta G in joules because of R. R is joules per mole Kelvin, so make sure you've performed that unit conversion before finishing your math. So after we've plugged in our delta G in joules by multiplying by 1,000 to match our R, that is joules per mole Kelvin, we can divide both sides by R and T. We get L and K is equal to 216.74. We can raise e to the power of each of those things to cancel out that L and K to find our K value here. We get 1.35 times 10 to the 94th power, which is way, way bigger than 1. Because of that really large K plus our negative G, we know that this reaction is most definitely thermodynamically favorable because, again, both negative delta G and K greater than 1 are going to indicate this. So there's some more practice that we'll be working on with Gibbs free energy that you can try out over the next couple of pages.